Traveller, something quiet has drawn you into this hour as if the cosmos itself paused and waited for your attention. You weren't meant to pass by this night untouched. A subtle alignment of time and motion has brought you here, where silence carries more meaning than noise. What are the odds that at the exact moment Earth's systems dimmed and data streams went dark, an interstellar body crossed the observing window of Mars, drifting, just close enough for our instruments to watch, yet not speak? What if that absence was not empty at all, but full of unrecorded detail? Now everything slows. A distant shape glides past the red edge of Mars. Cameras remain still. Space exhales. Stay with me. Let's drift a little deeper. In the early hours of October 1st, 2025, the machinery of the United States government slowed to a halt. Funding expired, federal agencies suspended, public operations and official websites froze in place. NASA's familiar stream of updates, images and explanations went silent. There were no alarms or announcements, only absence of procedural pause rooted in law and not spectacle. At the same moment, far beyond Earth's administrative boundaries, an object that did not originate in our solar system entered a critical observational geometry near Mars. Designated 3I Atlas. It is only the third confirmed interstellar visitor ever detected passing through our planetary neighbourhood. Its trajectory is hyperbolic, unbound to the sun, marking it as a traveller that arrived from elsewhere and will never return. The coincidence was precise. As public-facing NASA communications ceased, 3I Atlas moved within roughly 30 million kilometres of Mars, close enough by astronomical standards for orbiters circling the planet to conduct coordinated observations. These spacecraft carry instruments capable of analysing reflected light, dust gas composition and motion with extraordinary sensitivity. For a brief window, Mars held a clearer view of the object than Earth would for months. From Earth's surface, observations were limited. The object's position relative to the Sun placed it in a region of glare that overwhelmed most ground-based telescopes. Mars, however, occupied a favourable vantage point. Cameras were already scheduled. Pointing geometries had been calculated weeks in advance. The encounter was expected, not sudden. What changed was the human context surrounding it. NASA's silence was not mysterious in a legal sense. During a shutdown, non-essential public communication stops by statute. Data may still be collected, stored and processed internally, but outward-facing channels remain inactive. Historically, this has happened before during budget standoffs, policy impasses, and funding lapses that briefly interrupt the public rhythm of science. What made October 2025 different was timing. Interstellar objects are rare. Planetary flybys by such objects are rarer still. The overlap between a shutdown and one of the most scientifically valuable moments in recent small body astronomy was statistically unlikely, even if not impossible. Meanwhile, other space agencies continued openly. The European Space Agency, operating under different funding structures, confirmed observation plans and discussed orbital geometry publicly. The contrast was noticeable. One institutional voice continued steadily while another fell quiet, not because the sky was empty, but because governance had paused. In the absence of official updates, speculation emerged. Some observers assumed suppression, others delay, others nothing more than bureaucratic inconvenience. History offers examples of all three dynamics, though rarely cleanly separated. Scientific silence, even when procedural, has a long record of inviting narrative to fill its gaps. None of this implies intent or concealment. It illustrates something older and more persistent: the friction between human systems and cosmic events. The universe does not align its most interesting phenomena with political calendars. Celestial mechanics operate independently of budgets, elections, and legislation. When those timelines intersect, the result often feels unsettling. 3A Atlas continued on its path regardless. It passed, Mars moved deeper toward perihelion and slipped gradually back into observational difficulty. Whether the data gathered during that window will revise existing models or simply refine them remains a matter of analysis, not speculation. What endures is the lesson itself. Moments of genuine scientific importance do not always arrive with clarity or commentary. Sometimes they unfold during silence recorded quietly, by machines orbiting another world while attention on Earth is briefly elsewhere. The days following the Mars flyby unfolded without dramatic revelation, yet they carried a quiet weight familiar to historians of science. When communication resumes after an institutional pause, attention naturally shifts forward. What was missed is rarely examined with the same intensity as what comes next. In the case of 3I Atlas, this tendency mattered because interstellar objects do not linger. Their value lies not in prolonged study but in narrow windows, where geometry light and instrumentation briefly align. By mid-October 2025, analysis resumed across multiple observatories. Orbital solutions refined the object's path with increasing precision, confirming what had already been suspected. 3I Atlas followed a trajectory unbound to the Sun, with an eccentricity far beyond anything produced by native solar system dynamics. This alone placed it in a category of exceptional interest. Hyperbolic visitors carry with them information about environments far beyond our own stellar neighbourhood, preserving chemical and structural clues formed under different conditions of radiation pressure and time. Spectroscopic observations gathered both before and after the Mars encounter deepened the puzzle. The object exhibited activity at distances where most comets remain largely inert. Carbon-bearing molecules dominated its emissions, while water signatures appeared unexpectedly weak. Similar behaviour had been noted in earlier interstellar visitors, yet not to this degree. Each new data point strained existing classification schemes that comfortably separate comets, asteroids and transitional bodies. Mars orbiters played a subtle but important role here. Even without publicly released imagery during the shutdown window, their positional advantage allowed them to collect light curves and motion data less affected by solar glare. Such measurements are not visually dramatic, but they are foundational. Slight variations in brightness over time reveal rotation states. Deviations from predicted motion hint at non-gravitational forces such as outgassing. In the case of 3I Atlas, those deviations were present but restrained, suggesting either a substantial mass or a distribution of activity unlike typical cometary behaviour. This raised a fundamental question familiar to planetary science: how representative are our models when applied beyond the solar system? For centuries, astronomy advanced under the assumption that the processes shaping our planetary neighbourhood were broadly universal. Interstellar objects challenge that assumption. They're not samples of our outskirts but of elsewhere. Each one tests whether the categories we rely on are descriptive truths or convenient approximations. Historically, moments like this are rarely resolved quickly. When Uranus was first observed, it was mistaken for a star. When meteorites were proposed as extraterrestrial in origin, the idea was dismissed as superstition. Even the existence of galaxies beyond the Milky Way was debated well into the 20th century. The pattern is consistent. Anomalous data appears first as an inconvenience, then as a curiosity, and only later as a catalyst for revised understanding. The public reaction to 3I Atlas followed a parallel arc. In the absence of immediate clarity, narratives multiplied. Some framed the shutdown timing as deliberate obstruction, others as irrelevant coincidence. Both perspectives shared a common feature: they interpreted silence as signal. Yet in scientific history, silence is more often procedural than conspiratorial. Data pipelines take time, verification demands patience. Extraordinary claims, if entertained at all, require proportionally rigorous evidence. What is more instructive than speculation is the structural fragility revealed by the episode. Modern science depends not only on instruments and expertise, but on continuity of governance. Spacecraft do not cease orbiting when budgets lapse, but the human systems that contextualize their observations can and do pause. This creates asymmetries in perception, where discovery continues quietly while interpretation stalls. In earlier eras, such delays were common and largely invisible. Observations recorded on photographic plates might sit unanalyzed for years. Letters between observatories took months to arrive. Today, expectation has shifted. Real-time updates are assumed. When they fail to appear, absence itself becomes noteworthy. The shutdown surrounding the Mars flyby highlighted this cultural shift more than any anomaly in the data. As October progressed, 3I Atlas moved closer to perihelion, its behaviour evolving under increasing solar influence. Activity levels changed, tails formed and dissipated, and its brightness fluctuated in ways broadly consistent with volatile-driven processes. No single observation overturned existing physical laws. Instead, the object added weight to a growing realization. Interstellar bodies are not rare curiosities, but an undersampled population, one that future surveys will detect with increasing frequency. From a historical perspective, this reframes the significance of the Mars encounter. It was not a singular revelation, but an early chapter in a longer narrative. The importance of such moments often becomes clear only retrospectively when later discoveries provide context. What appears ambiguous today may later be recognised as the first hint of a broader pattern. The episode also underscores a quieter truth. Scientific progress does not require drama to be meaningful. It advances through incremental measurements, cautious interpretation, and the willingness to revise assumptions. 3i Atlas did not announce itself as a revolution. It behaved largely like matter responding to physics. Its strangeness lay not in defiance of law, but in its reminder that our sample size is small and our confidence provisional. In the end, the convergence of an interstellar flyby and a governmental shutdown revealed more about human systems than cosmic ones. The object passed as expected, indifferent to politics, procedure, or perception. What remained was a record of how observation, interpretation, and uncertainty interact when rare events meet imperfect institutions. Such moments are neither warnings nor revelations. They are mirrors. They show how much of science depends on context, timing, and patience. And they suggest that as more visitors like 3i Atlas pass through our sky, the challenge will not be detecting them, but learning to understand them without projecting meaning where none is yet justified. As 3i Atlas continued its passage through the inner solar system, the focus gradually shifted from circumstance to substance. With orbital data stabilized and observation windows narrowing, attention turned toward interpretation rather than timing. This transition is familiar in the history of astronomy. Once the rare alignment has passed, what remains is evidence incomplete and often resistant to simple explanation. One of the most persistent questions surrounding interstellar objects concerns origin. Unlike asteroids or comets native to the solar system, these bodies are fragments of other stellar environments. Their chemical makeup reflects conditions that may differ significantly from those present during the Sun's formation. In the case of 3i Atlas, spectroscopic measurements suggested an abundance of carbon-rich compounds relative to water, alongside signatures of activity at heliocentric distances that would normally suppress such behaviour. While not unprecedented, the combination was unusual enough to warrant careful scrutiny. These observations prompted renewed discussion about how interstellar material is processed before ejection from its parent system. Planetary migration, stellar radiation, and gravitational interactions all shape what ultimately escapes into interstellar space. Objects like 3i Atlas may therefore represent survivors of violent early epochs, bearing scars of close stellar encounters or planetary upheaval. Their apparent resilience to solar heating may reflect structural properties forged under harsher conditions than those typical of our own cometary population. Rotation and morphology also became subjects of analysis. Subtle periodic variations in brightness hinted at a non-spherical shape, possibly elongated or irregular, rotating slowly as it travelled sunward. Such forms are common among small bodies, yet in an interstellar context they acquire added significance. Shape influences thermal evolution, outgassing patterns and stability. It also constrains models of formation and fragmentation. Whether 3i Atlas formed as a monolithic body or as an aggregate remains uncertain, but its behaviour suggested internal cohesion, sufficient to survive both interstellar transit and solar approach. Non-gravitational forces provided another avenue for investigation. Active comets experience measurable deviations from purely gravitational trajectories as gas escapes their surfaces. For 3i Atlas, these effects appeared present but muted. This implied either a relatively large mass or a distribution of activity that balanced forces more evenly than expected. Such conclusions, while tentative, highlighted the limits of extrapolating from solar system analogues. Interstellar objects are shaped by histories we can only partially reconstruct. The broader scientific significance of these findings lies less in any single anomaly than in their collective implication. Each interstellar visitor challenges the assumption that our local inventory of small bodies is representative of what exists elsewhere. The solar system may be atypical in subtle but important ways, or it may simply reflect one outcome among many. Without comparative samples, certainty remains elusive. From a historical standpoint, this uncertainty is not a weakness, but a driving force. Astronomy has advanced repeatedly by confronting cases that defied classification. The realization that nebulae were distant galaxies, that quasars were extraordinarily energetic, extragalactic sources, and that planets existed around other stars all emerged from initially puzzling data. Interstellar objects belong to this lineage of disruptive observations, modest in appearance yet expansive in implication. Public discourse, however, often seeks definitive answers where science offers only probabilities, in the case of Through Eye Atlas. Speculation ranged from mundane to extravagant, fueled in part by the earlier communication gap. Such reactions are understandable. When phenomena are rare and data sparse, narrative fills the void. Yet history suggests caution. Premature conclusions tend to obscure rather than illuminate. What the passage of Three Eye Atlas ultimately demonstrated was not the presence of hidden intent or extraordinary agency, but the complexity of interpreting limited information. Instruments capture light spectra and motion, but meaning emerges only through careful comparison modelling and peer review. This process is slow by design, resistant to immediacy, and often unsatisfying to those seeking closure. Looking ahead, the importance of this episode becomes clearer in light of upcoming surveys. Next-generation telescopes are expected to detect interstellar objects, more frequently transforming them from curiosities into a recognised population. When that happens, the questions raised by Three Eye Atlas will no longer be exceptional. They will become part of a systematic effort to understand the diversity of planetary systems beyond our own. In that future context, the Mars flyby and the surrounding silence may appear as a transitional moment. Not because something was hidden or revealed, but because it marked the point at which interstellar astronomy shifted from novelty to necessity. The limitations exposed by that week underscore the need for resilient scientific infrastructure capable of continuity regardless of political or administrative interruption. As 3 Atlas receded from favourable viewing geometry and continued on its irreversible path back into interstellar space, it carried with it no message and left behind no verdict. It offered instead a reminder of scale. Human institutions operate on cycles measured in years or decades. Celestial dynamics unfold across millions of years indifferent to the frameworks we impose upon them. In this sense, the most enduring lesson of 3 Eye Atlas is methodological rather than philosophical. It reinforces the value of restraint, of distinguishing what is known from what is inferred, and of accepting uncertainty as an intrinsic feature of exploration. The object's passage did not resolve long-standing debates about the nature of interstellar bodies, it sharpened them. History will likely record 3 Atlas as one of many early interstellar visitors, noteworthy not for singular revelations, but for its contribution to a gradual expansion of perspective. Each such object adds a data point, a constraint, a challenge. Together they will redefine how planetary science understands its place within the broader galactic environment. When future researchers look back on this period, they may see October 2025 not as a moment of mystery, but as a case study in how science adapts when the universe offers something unexpected and fleeting. In that adaptation lies progress measured not by certainty, but by the willingness to continue observing, questioning, and refining what we think we know. As attention gradually moved away from the immediate observations of 3 Eye Atlas, a deeper question emerged that extended beyond this single object. What does it mean for planetary science when visitors from other star systems are no longer theoretical but observable realities? The answer is not dramatic, but it is profound. It requires a reassessment of how knowledge is built when evidence arrives briefly and perfectly and without repetition. For most of scientific history, astronomy relied on permanence. Stars returned night after night. Planets followed predictable paths. Even comets, once feared and misunderstood, revealed periodic behaviour that allowed them to be studied across generations. Interstellar objects disrupt this rhythm. They arrive, once pass quickly and vanish forever. There are no second chances. Every measurement must be made in real time under constraints imposed by geometry, technology, and chance. This scarcity places unusual pressure on interpretation. When data is limited, the temptation to overextend conclusions increases. The history of science is crowded with examples where early observations were forced into existing frameworks only to be corrected decades later. Interstellar astronomy risks repeating this pattern if restraint is not maintained. 3-Somike Atlas highlighted this risk precisely because it sat at the boundary between familiarity and novelty. On one hand, the object displayed behaviour broadly consistent with known physical processes. Solar heating drove activity, volatile compounds sublimated, light reflected and scattered according to established laws. On the other hand, the proportions, timing and persistence of these effects did not align cleanly with expectations derived from solar system bodies. The discrepancy was not radical but persistent enough to matter. Such tensions are historically productive. They signal regions where theory remains incomplete. In the 19th century, anomalies in Mercury's orbit pointed toward limitations in Newtonian mechanics. In the 20th, irregularities in stellar spectra hinted at nuclear processes unknown at the time. In neither case did the anomaly immediately reveal its cause. It simply refused to disappear. 3I Atlas occupies a similar though more modest position. It does not demand a new physics, but it does suggest that the diversity of small bodies in the galaxy exceeds what solar system-centric models predict. This realization has implications beyond academic classification. It affects estimates of material exchange between star systems, the frequency of planetary disruption, and the long-term evolution of galactic matter. From a historical perspective, the study of meteoritics offers a useful parallel. For centuries, stones falling from the sky were dismissed as folklore. Only when physical samples accumulated did consensus shift. Even then, classification systems evolved, slowly reshaped by each new find. Interstellar objects represent a similar phase but without the luxury of retrieval. They are samples we can observe but never touch. The institutional response to this challenge is still forming. Space agencies, observatories and survey programs are adapting to a reality where detection speed matters as much as sensitivity. Rapid alerts, automated follow-up, and international coordination are becoming essential. The episode surrounding the Mars flyby underscored how fragile this coordination can be when human systems falter even briefly. Yet the long-term trajectory is clear. Future discoveries will benefit from lessons learned during 3I Atlas. Observation strategies will be refined. Data sharing protocols will be strengthened. Expectations will become more realistic. In this sense, early interstellar visitors serve not only as scientific targets, but as stress tests for the infrastructure of modern astronomy. The public dimension of this process cannot be ignored. Rare events invite meaning-making beyond evidence. Throughout history, celestial phenomena have been interpreted as omens, messages, or interventions. Modern language is more technical, but the impulse persists. When explanations are delayed or incomplete speculation fills the gap, the responsibility of science is not to eliminate curiosity, but to guide it without surrendering rigour. 3 Atlas ultimately resisted narrative simplification. It was neither mundane enough to ignore, nor extraordinary enough to redefine understanding on its own. Its value lay in accumulation, not revelation. Each spectrum, each positional refinement, each brightness curve contributed incrementally to a broader picture that remains unfinished. As the object receded beyond practical observation, attention shifted towards synthesis. Papers were drafted, models adjusted, uncertainties acknowledged. This phase is rarely visible outside academic circles, yet it is where meaning stabilizes. The excitement of detection gives way to the discipline of interpretation. In historical hindsight, this is often where true progress occurs. The lasting importance of 3I Atlas may therefore be temporal rather than transformational. It arrived at a moment when detection capabilities were sufficient to notice it, but interpretive frameworks were still evolving. It exposed gaps, not because it was anomalous, but because it was unfamiliar. That distinction matters. Anomalies demand explanation. Unfamiliarity demands patience. In future decades, as more interstellar objects or catalogue patterns will emerge, statistical distributions will replace singular impressions. What now appears unusual may become typical, or it may remain rare, pointing towards specific formation pathways that only occasionally intersect with our solar system. Either outcome depends on data yet to be gathered. Seen from that future vantage point, part 4 of this story is not an ending but a pause, a moment where observation outpaced understanding and restraint proved more valuable than certainty. The passage of 3 Atlas did not resolve deep questions about the galaxy. It clarified where those questions begin, and in the long arc of scientific history, that clarification is often the quiet beginning of knowledge rather than its conclusion. By the time 3 Atlas faded from meaningful observation, what remained was not an answer, but a recalibration. Scientific events of this kind rarely conclude with resolution. Instead, they alter the baseline against which future evidence is judged. The object's passage forced planetary science to confront a transitional moment, one in which rarity no longer guarantees exception, and novelty no longer implies anomaly. For decades, interstellar objects were treated as theoretical possibilities, rather than practical research targets. Models predicted their existence, but detection remained improbable. Survey sensitivity was insufficient, coverage incomplete, and the expected frequency low. The discovery of 3I Atlas following 2 earlier visitors within a single decade weakened those assumptions. It suggested not that interstellar objects had suddenly increased in number, but that human observation had finally crossed a threshold. This shift carries methodological consequences. When phenomena are rare, they are interpreted individually. Each case becomes a narrative. When they become detectable with some regularity, comparison replaces storytelling. Patterns begin to matter more than singular features. 3I Atlas occupies an uncomfortable position between these modes, discovered too early to benefit from statistical context, yet too late to be dismissed as a one-off curiosity. Its behaviour highlighted the danger of overfitting explanation to limited data. Every interstellar object detected so far has been forced, at least initially, into analogies drawn from solar system bodies. Comet-like, asteroid-like, transitional. These labels are useful, but they are also restrictive. They assume that the processes shaping our neighbourhood are representative of galactic norms. That assumption is increasingly difficult to defend. Planetary systems form under a wide range of conditions. Stellar mass metallicity, radiation environment, and dynamical history all influence the architecture of planets and debris. Objects ejected from such systems carry that diversity with them. When they pass through our solar system, they are not obliged to conform to expectations built from local examples. 3 Atlas did not violate physical law. It simply refused to behave conveniently. From a historical perspective, this moment resembles earlier expansions of scale in astronomy. When exoplanets were first confirmed, they confounded existing models. Hot Jupiters, super-Earths, and compact multi-planet systems challenged assumptions derived from a single example. Over time, theory adapted. The same process is now beginning at the level of small bodies where interstellar samples promise to reveal how common or unusual our own system truly is. The institutional lessons of the 3I Atlas episode are equally significant. Science operates within social structures that are rarely optimized for fleeting phenomena. Funding cycles, administrative boundaries, and national jurisdictions all introduce friction. The Mars flyby occurred during a period when that friction became visible. Data collection did not stop, but interpretation slowed, communication fractured, and public understanding drifted. This is not an argument for attributing intent or concealment. It is an observation about vulnerability. When scientific opportunity depends on continuous coordination, even brief disruptions matter. As detection rates increase, the need for resilient, internationally integrated response systems will become unavoidable. Interstellar objects do not respect borders. Their study cannot afford to be constrained by them. Public reaction to 3I Atlas also revealed a persistent tension between curiosity and certainty. Many observers were less interested in what could be responsibly concluded than in what might be possible. This impulse is not new. Throughout history, moments at the edge of knowledge have attracted speculation disproportionate to evidence. The challenge for science is not to suppress that impulse, but to contextualize it. What makes interstellar objects particularly susceptible to misinterpretation is their ambiguity. They are distant, brief, and unrepeatable. They arrive without precedent and leave without confirmation. This makes them fertile ground for projection. Yet history shows that enduring understanding emerges not from dramatic claims, but from cumulative restraint. In the months following the passage of 3 Atlas, the scientific conversation became quieter. Papers focused on refining orbital parameters, modelling activity, and comparing results with previous interstellar detections. None claimed definitive conclusions. Instead, they emphasised uncertainty ranges, alternative explanations, and the need for future data. This is often mistaken for indecision. In reality, it is the discipline that prevents error from hardening into belief. The most important outcome of the event may therefore be conceptual rather than empirical. 3I cis Atlas reinforced the idea that planetary science is no longer confined to the solar system. Small bodies are messengers of galactic processes, not merely local debris. Their study requires a mindset willing to accept that familiar categories may dissolve when confronted with broader context. As detection capabilities continue to improve, future interstellar objects will arrive under different circumstances. Some will be found earlier, some will pass closer. Some may display behaviour that fits existing models more neatly, others may challenge them further. The significance of 3I Atlas lies in its position near the beginning of this transition, when uncertainty still outweighs expectation. In retrospect, October 2025 may be remembered less for what was seen than for how science responded. An interstellar visitor passed through during a moment of institutional quiet, exposing both the strengths and limitations of modern observation. The object itself did not demand extraordinary explanations, it demanded better questions. That is often how scientific progress begins, not with revelation but with discomfort, with evidence that fits imperfectly, with the realization that existing frameworks, while functional, are incomplete. 3I Atlas offered no answers about purpose, origin, or meaning beyond physics. What it offered instead was a clearer view of how much remains unknown. And in that recognition, the trajectory of inquiry subtly shifted. Not toward certainty, but toward preparedness. Not toward narrative closure, but toward continuity. The object is gone, but the questions it sharpened remain waiting for the next visitor from beyond the sun to carry them further. As the discussion surrounding 3I Atlas settled into technical literature, its broader implications continued to unfold in quieter ways. Scientific progress is often measured by discovery, yet equally important is the refinement of expectation. Events like this recalibrate what researchers consider normal, plausible, or worthy of attention. In that sense, the passage of 3 Atlas marked not an endpoint, but an adjustment in how interstellar phenomena are framed. One of the clearest outcomes was a reassessment of observational readiness. Interstellar objects move quickly, appear with little warning, and often occupy unfavourable positions in the sky. Their study demands rapid coordination across telescopes, wavelengths, and institutions. The experience of October 2025 exposed both strengths and gaps in that system. Instruments performed as designed. Survey pipelines detected the object in time. Where strain appeared was in continuity, the ability to maintain seamless interpretation and communication under changing human conditions. Historically, astronomy has adapted to similar challenges by building redundancy. Multiple observatories, overlapping surveys, and independent analysis pathways reduce reliance on any single node. Interstellar astronomy will likely follow this pattern. Automated response protocols, shared alert systems, and pre-approved observation plans can mitigate delays. The lesson of 3I Atlas is not that the system failed, but that it was tested earlier than expected. At a theoretical level, the object encouraged renewed focus on population modelling. If interstellar visitors are more common than previously assumed, then their distribution size range and composition become measurable quantities rather than abstractions. Early estimates were constrained by detection bias. Larger, brighter objects were easier to find, skewing perception. As sensitivity improves, smaller and fainter visitors will enter the dataset, reshaping those distributions. This transition mirrors earlier developments in asteroid science. Once thought to be sparse and unimportant asteroids became central to understanding solar system formation as surveys expanded. The same shift is now underway on a galactic scale. Interstellar objects are not exotic anomalies. They are debris natural byproducts of planetary evolution elsewhere. Their rarity was an artifact of our blindness. Doi Atlas also highlighted the interpretive challenge of incomplete sampling. With only a handful of confirmed interstellar objects, every comparison carries disproportionate weight. Similarities may reflect common processes, or they may be coincidental. Differences may indicate diversity, or simply observational bias. Recognizing this ambiguity is essential. Premature generalization risks building frameworks that future data will dismantle. From a historical standpoint, the early phase of any new observational domain is marked by such instability. Radio astronomy, X-ray astronomy, and exoplanet studies all passed through periods where anomalies outnumbered explanations. Over time, coherence emerged not because the universe became simpler, but because datasets became richer. Interstellar astronomy stands at a comparable threshold. The public narrative surrounding 3i Atlas gradually faded as newer events captured attention. This too follows a familiar pattern. Scientific significance does not always align with sustained visibility. Many discoveries that later proved foundational were initially met with indifference once immediate novelty passed. Their influence was felt indirectly, shaping methods, priorities, and assumptions rather than headlines. In academic contexts, the object's legacy became more concrete. It informed proposals, justified funding for rapid response programs, and reinforced arguments for continuous sky monitoring. It also provided a case study in how scientific communication interacts with institutional interruption. While the shutdown was procedural, its overlap with a rare event underscored the need for continuity mechanisms that preserve transparency, even when governance pauses. At a deeper level, 3i Atlas prompted reflection on the relationship between certainty and curiosity. The object did not resolve questions about interstellar chemistry formation environments or population statistics. Instead, it clarified which questions are answerable and which remain open. This distinction matters. Productive science advances by narrowing uncertainty, not eliminating it. The object's final departure from observation carried a subtle irony. After weeks of speculation and analysis, it returned to the state from which it emerged, a point of light, indistinguishable from countless others, receding into the background of the galaxy. Its physical presence vanished, but its conceptual impact persisted. It expanded the scope of what planetary science considers relevant. Future interstellar visitors will arrive under different conditions, and their study will benefit from the groundwork laid by early cases. They will be detected sooner, tracked more comprehensively, and interpreted with frameworks shaped by experience. When that happens, 3i Atlas will be remembered not as an outlier, but as part of a formative sequence. In the long arc of scientific history, such sequences matter more than singular events. They mark transitions from assumption to observation, from theory to evidence. 3i Atlas belongs to this category. It did not change what physics allows. It changed what scientists expect to encounter. The lasting contribution of the object lies in that shift of expectation. It reminded researchers that the solar system is not an isolated laboratory, but a porous boundary through which material from elsewhere occasionally passes. Each passage carries information shaped by distant stars and unseen histories. As planetary science continues to expand beyond local confines, encounters like 3i Atlas will become reference points rather than curiosities. They will define the early era of interstellar observation when the first data points arrived and the discipline learned how to respond. As the scientific community reflected on the passage of 3i Atlas, attention gradually shifted from the object itself to the assumptions it quietly challenged. Encounters with interstellar visitors do more than add data points. They expose how strongly modern astronomy still relies on local experience. For centuries, the solar system has served as the primary reference for understanding planetary debris, shaping expectations about composition, structure, and behaviour. Objects arriving from beyond that system reveal the limits of such extrapolation. The solar system is not a template, but a case study. Its small bodies formed under specific conditions, a particular stellar mass metallicity radiation environment, and dynamical history. interstellar objects carry the imprint of different circumstances shaped by stars that may be hotter, cooler, older, or chemically distinct. When such objects pass through our observational reach, they confront theory with diversity rather than contradiction. The challenge is not that existing models are wrong, but that they are incomplete. In this light, 3I Atlas served as a calibration point. Its activity profile, chemical signals, and apparent resilience under solar heating did not violate physical law. Instead, they occupied a boundary region where expectations softened into uncertainty. This boundary is historically significant. Many advances in astronomy have emerged not from dramatic anomalies, but from persistent misalignments between prediction and observation. Such misalignments signal where knowledge ends and inquiry begins. A parallel can be drawn with the early study of stars. For a long time, stars were treated as broadly similar objects, differing mainly in brightness and distance. Only with improved spectroscopy did classification systems reveal their true diversity, transforming stellar astronomy into a science of populations rather than exemplars. Interstellar objects may represent a comparable transition for planetary science, shifting focus from isolated cases to comparative context. Another layer of significance lies in the role of automation. Modern surveys operate continuously scanning vast regions of sky and identifying transient phenomena with unprecedented efficiency. The discovery of 3I Atlas was not the result of targeted observation, but of algorithmic vigilance. Machines recognized motion inconsistent with bound solar system orbits long before humans could contextualize it. This marks a fundamental change in how discovery occurs, yet detection alone does not constitute understanding. Automated systems excel at identifying anomalies, but interpretation remains a human task shaped by caution, precedent, and debate. The interval between detection and comprehension can be uncomfortable, especially when public awareness outpaces scientific consensus. In the case of 3I Atlas, this gap was amplified by silence procedural rather than intentional, but consequential nonetheless. Such dynamics are likely to intensify. As survey capabilities expand, interstellar detections will become more frequent. Each will arrive with limited data, brief observation windows, and incomplete context. The risk is not in the data itself, but in the narratives imposed upon it prematurely. History offers ample warning. From canals on Mars to early claims of faster-than-light particles, scientific meaning has often been distorted when interpretation raced ahead of verification. The responsibility of science in these moments is not to provide immediate closure, but to maintain disciplined uncertainty. This is a difficult posture in an environment that rewards certainty and speed. Yet it is essential. Interstellar objects do not repeat. There is no opportunity for controlled experiment or revisit. Each encounter must be interpreted with restraint, acknowledging what is known, what is inferred, and what remains unresolved. Institutionally, the episode highlighted the fragility of continuity. Spacecraft continued to operate, data continued to accumulate, but public interpretation stalled. This separation between observation and communication created a vacuum that speculation quickly filled. While such speculation is not new, its amplification reflects modern expectations of immediacy. The lesson is structural rather than conspiratorial. Scientific systems must adapt to ensure transparency, even under interruption. Beyond logistics, the encounter also reframed humanity's relationship to its environment. Interstellar objects remind us that the solar system is not sealed. Material flows between stars, carrying fragments of distant histories through interplanetary space. This exchange has likely occurred for billions of years, unnoticed until recently. The realization does not diminish Earth's significance, but it situates it within a more dynamic galactic context. The absence of definitive conclusions about 3I Atlas is not a failure. It is a reflection of scale. Understanding the galaxy cannot be achieved through singular events, no matter how intriguing. It emerges through accumulation, comparison, and patience. Each interstellar visitor contributes incrementally, shaping expectations for the next. Over time, patterns will replace impressions. In retrospect, the importance of 3I Atlas may lie less in its specific properties than in its timing. It arrived at a moment when detection capabilities were sufficient but interpretive frameworks were still adapting. It exposed gaps between observation communication and understanding. It revealed how quickly uncertainty can be filled with meaning and how necessary restraint remains. As future detections add depth to the dataset, early cases like this one will gain clarity through context. What now appears ambiguous may later seem ordinary, or it may stand out as an early signal of diversity not yet fully mapped. Either outcome affirms the same principle: scientific understanding advances not through immediate answers, but through disciplined engagement with uncertainty. The passage of 3i Atlas did not announce a transformation of physics or confirm extraordinary hypotheses. It did something quieter and more enduring. It reminded observers that the universe is larger, more varied, and less obligated to conform to expectation than any single system suggests. That reminder, grounded in evidence rather than speculation, is where progress begins. As time passed, and discussion around 3i Atlas receded from immediate attention, its deeper significance began to surface in a more subtle form. Scientific understanding rarely changes in sharp turns. More often, it drifts guided by accumulated experience rather than singular events. Objects like this one exert influence not by what they reveal outright, but by how they reshape the questions scientists are willing to ask. One of the most enduring shifts prompted by interstellar encounters is conceptual rather than technical. For much of the modern astronomy, the boundary of the solar system functioned as an implicit limit. Beyond it lay abstraction, distant stars, theoretical disks, statistical populations inferred rather than observed. Interstellar objects collapse that boundary. They are tangible evidence that material formed elsewhere can and does cross into our observational domain. The galaxy is not merely a backdrop, it is an active participant. This realization alters the scale at which planetary science operates. Small bodies are no longer viewed solely as remnants of local formation, but as part of a wider exchange of matter between star systems. Ejection events, once treated as losses, become mechanisms of distribution. Collisions, migrations, and instabilities in distant systems do not end at their stars. They echo outward, seeding interstellar space with debris that may one day pass another sun. Within this framework, 3i Atlas becomes less mysterious and more instructive. Its properties, whether typical or unusual, gain meaning only when placed against a backdrop of many such objects. At present, that backdrop is thin. Each detection carries disproportionate interpretive weight. This is a temporary condition, characteristic of early observational eras. As sample sizes grow, emphasis will shift from explanation of individuals to characterization of populations. The transition from individual to population-based science has repeated itself across disciplines. Early paleontology revolved around singular fossils. Early genetics focused on a handful of traits. Early cosmology grappled with a few distant galaxies. In each case, understanding deepened only when numbers increased. Interstellar astronomy is entering its equivalent phase, and 3i Atlas belongs to that formative interval. Another consequence of this transition concerns expectations of predictability. Solar system objects follow well-mapped distributions shaped by billions of years of evolution under a single star. Interstellar objects arrive without such context. Their paths are shaped by encounters long past, often irrecoverable. This makes prediction difficult and demands flexibility in interpretation. Uncertainty is not a temporary inconvenience, but an intrinsic feature of the domain. This has implications for how evidence is communicated. In mature fields, uncertainty is bounded. Error bars are familiar. In emerging ones, uncertainty is structural. It affects not only measurements, but categories themselves. When this distinction is not made clear, misunderstanding follows. The public response to rare celestial events often reflects a desire for definitive explanation, where none yet exists. History shows that this tension is persistent. New domains of observation tend to attract meaning beyond their evidentiary content. Early telescopic observations of the Moon were interpreted through theological and philosophical lenses. Comets were read as portents long after their orbits were understood. Even today, unfamiliar phenomena invite symbolic interpretation alongside scientific inquiry. The challenge is not to suppress this tendency, but to separate it from evidence-based conclusions. 3i Atlas demonstrated how easily that boundary can blur. Limited data, rare timing, and procedural silence created conditions ripe for projection. Yet the object itself remained indifferent to interpretation. It followed its trajectory, responded to solar energy, and departed. The universe offered no commentary. Meaning was supplied entirely by observers. This asymmetry is worth noting. Scientific phenomena do not arrive with narrative. Narrative is constructed afterward, shaped by context, expectation, and absence. Recognizing this does not diminish the value of storytelling, but it clarifies its role. Storytelling organizes curiosity, science constrains it. As interstellar detections become more frequent, maintaining this balance will become increasingly important. Routine encounters will reduce novelty but increase responsibility. Each object will still be unique yet less singular. The temptation to overinterpret will persist, but it will compete with a growing archive of comparative data. At an institutional level, the long-term effect of 3i Atlas may be cultural. It highlighted the need for preparedness not only in instrumentation but in communication. Scientific credibility depends on consistency and clarity, especially when events are fleeting. Interruptions, even when mundane, distort perception. Building systems that preserve transparency across such interruptions is not a luxury. It is an adaptation to reality. Beyond institutions, there is a quieter shift in perspective. Interstellar objects encourage humility. They remind observers that local knowledge is partial, that the solar system is one expression among many, and that extrapolation carries risk. This humility is not resignation. It is a productive stance that keeps inquiry open rather than fixed. The absence of final answers about 3i Atlas is therefore appropriate. It reflects the scale of the question rather than the inadequacy of the data. Understanding galactic diversity will require decades of observation, comparison, and revision. Early encounters will always appear ambiguous in hindsight. Their role is to open paths, not close them. As astronomy moves forward, future interstellar visitors will be detected earlier, tracked longer, and analysed with refined tools. Some will align neatly with expectation, others will not. Each will contribute incrementally to a picture that remains under construction. When that picture gains coherence, early cases will acquire retrospective clarity. Until then, the lasting impact of 3i Atlas lies in adjustment. It adjusted assumptions about rarity. It adjusted confidence in local models. It adjusted awareness of how human systems interact with cosmic events. These adjustments are quiet, but they endure. The object has long since passed beyond reach, indistinguishable, now from countless others travelling between stars. What remains is a recalibrated understanding of what it means to observe the universe, as it is rather than as we expect it to be. In that recalibration, progress continues not marked by revelation but by patience. As attention shifted away from immediate observation and toward interpretation, a deeper question emerged about how knowledge itself is filtered, delayed, and sometimes distorted before it reaches public understanding. The case of 3i Atlas did not introduce new physics, but it exposed old tensions between discovery and disclosure. These tensions are not unique to astronomy. They appear wherever scientific systems intersect with bureaucracy, funding structures, and institutional habit. Modern space science operates on layers. At the surface is public communication, press releases, images, summaries designed for broad audiences. Beneath that lies the operational layer where spacecraft are commanded, data is received, and instruments are monitored. Deeper still is analysis, where specialists work slowly through calibration, modelling, and interpretation. Each layer moves at a different speed, guided by different incentives. When those speeds fall out of alignment, confusion fills the gap. 3i Atlas passed through such a gap. The object itself followed a predictable path, but the human systems observing it did not move smoothly. Funding interruptions, communication pauses, and procedural constraints created a mismatch between what was happening and what was visible. The result was not secrecy in the strict sense, but opacity born of structure. This distinction matters because misunderstanding structure often breeds suspicion where none is required. Historically, scientific opacity has rarely been intentional. More often, it arises from specialization. data formats are complex, terminology is precise, interpretation requires context. When information is delayed or presented incompletely, it can appear withheld even when it is merely unprocessed. In an age of rapid information exchange, patience becomes scarce, and delay itself is treated as evidence. Astronomy has faced this pattern before. During the early days of space exploration, satellite failures were sometimes misinterpreted as cover-ups. In planetary science, mission delays have fueled speculation unrelated to evidence. Each time the underlying cause was mundane engineering, complexity, institutional caution, or limited manpower. Yet perception does not respond to explanations offered after the fact. It responds to silence in the moment. The challenge is compounded by the rarity of interstellar objects. Because they are uncommon, each instance attracts disproportionate attention. Normal procedural delays tolerable for routine observations become magnified when the event itself feels singular. The same delay that would pass unnoticed for a minor asteroid becomes suspect when applied to a visitor from beyond the solar system. This imbalance between expectation and process is structural, not personal. Scientists working on missions do not control funding cycles. Engineers maintaining spacecraft do not dictate communication policy. Analysts processing data do not decide when public statements are issued. Responsibility is distributed and accountability becomes diffuse. From the outside, however, the system appears monolithic, inviting assumptions of coordinated intent. Understanding this dynamic requires stepping back from individual events and examining patterns. When public communication pauses during administrative disruption, it does so across missions, not selectively. When data analysis slows, it affects many targets, not just unusual ones. Consistency across cases is the strongest indicator of procedural cause rather than deliberate suppression, yet consistency is rarely examined in moments of heightened attention. Singular events are treated as exceptional, even when governed by the same rules as everything else. 3 Atlas became a focal point, not because it was hidden, but because it arrived at a moment when the usual signals of transparency were muted. The absence of familiar reassurance amplified uncertainty. This raises a broader issue about how scientific institutions manage trust. Trust is not built solely on accuracy. It depends on continuity. Interruptions, even justified ones, erode confidence, if not anticipated by the public. In this sense, the event functioned as a stress test, revealing weaknesses in how expectations are managed rather than flaws in the science itself. There is also a psychological dimension. Human cognition is uncomfortable with incomplete narratives. When a story begins but does not resolve promptly, the mind fills gaps with conjecture. This tendency is ancient, predating science. Astronomy, despite its rigor, does not escape it. The more distant and unfamiliar the phenomenon, the stronger the impulse to supply meaning. Scientific training works against this impulse by privileging restraint. Conclusions are delayed until evidence converges, ambiguity is tolerated, but public discourse does not reward restraint. It rewards coherence, immediacy, and emotional resonance. When scientific silence meets narrative hunger, alternative explanations proliferate. This does not mean curiosity is misguided. It means curiosity operates differently across contexts. In research, curiosity drives methodical inquiry. In public discourse, it seeks resolution. The two are not aligned in time or structure. Bridging them requires intentional effort, especially when events are rare and fleeting. The long-term solution is not faster conclusions, but clearer framing of uncertainty. When institutions explain not just what they know, but why they do not yet know more, expectations adjust. Silence without context invites interpretation. Delay with explanation invites patience. The distinction is subtle, but consequential. In the case of 3I Atlas, much of the tension could have been reduced by acknowledging uncertainty explicitly and early, not by offering speculative answers, but by outlining the process, what data existed, what was pending, and why timelines were extended. Transparency about process often matters more than preliminary results. This lesson extends beyond astronomy. As science increasingly intersects with public interest, Especially in domains that touch existential themes, communication becomes part of the scientific ecosystem. Neglecting it does not preserve objectivity, it merely shifts narrative control elsewhere. Over time, the specifics of 3 Atlas will fade into archival records absorbed into datasets and comparative studies. What will persist is the memory of how the event felt sudden, rare, unresolved. That memory will shape responses to future interstellar detections. Expectations will be adjusted either toward greater patience or deeper suspicion depending on how institutions respond. The opportunity lies in learning. Interstellar objects are not going away. Detection rates will increase. Each new arrival will test not only instruments, but systems of interpretation. The goal is not to eliminate uncertainty, but to normalize it. When uncertainty is expected, it loses its power to unsettle. In the end, the object itself offers a quiet lesson. It did not announce its origin or explain its nature. It simply passed through, governed by forces indifferent to human schedules. The disturbance arose not from its behavior, but from the mismatch between cosmic timescales and human systems. Recognizing that mismatch is the first step toward adapting to it. As speculation accumulated, it became necessary to impose structure on uncertainty, rather than letting uncertainty dictate structure. When information is incomplete, disciplined comparison matters more than conviction. Competing explanations for the behavior of 3I Atlas did not arise from evidence alone, but from how humans respond to gaps in evidence. Sorting these explanations is not about choosing the most exciting story, but about understanding which ideas survive contact with method. The simplest explanation remains procedural coincidence. A funding lapse interrupted public communication, while an interstellar object passed through an observational window near Mars. Spacecraft continued operating. Data continued to exist. What paused was narration, not physics. This explanation aligns with documented policy historical precedent and the absence of verified contradictions in orbital data. It requires no hidden actors, no exotic materials, and no deviation from known institutional behavior. Its weakness is psychological rather than empirical. It feels unsatisfying because it attributes tension to timing rather than intent. A related explanation invokes transient environmental effects rather than administrative ones. Comets respond to their surroundings. Solar radiation increases as distance to the Sun decreases. Variations in solar wind density can trigger changes in outgassing. A coronal mass ejection striking a comet can temporarily brighten its coma or alter gas production. Mars itself, though distant at tens of millions of kilometers, contributes marginal gravitational influence. These effects are subtle but measurable. If small anomalies appear in brightness or activity during early October, they would not require unusual composition or intervention. They would fit comfortably within cometary physics. Another hypothesis centers on composition rather than circumstance. Early size estimates for 3I Atlas spanned a wide range which naturally translated into wide mass uncertainty. When mass is uncertain, density becomes speculative. Suggestions of a dense or metal-rich interior followed reports of nickel emission in the coma. Nickel, however, is not foreign to comets. Metallic atoms appear when dust grains are heated and release constituents. To argue for an unusually metal-heavy body requires quantitative abundance anomalies, not mere detection. Without consistent spectroscopy showing ratios far outside known cometary behavior, density-based conclusions remain premature. More extreme explanations depart from natural origins altogether. The idea that 3I Atlas might be engineered artificial or technological draws inspiration from earlier debates surrounding interstellar objects. Such hypotheses demand specific signatures, controlled acceleration, coherent electromagnetic emissions, structured rotation patterns or spectral features incompatible with natural materials. None of these have been confirmed. The burden of proof for artificiality is intentionally high, not because the idea is taboo, but because natural explanations must be exhausted first. At present, no published data requires abandoning natural models. A different speculative thread imagines intervention rather than origin. This view suggests that an advanced spacefaring actor, state or otherwise, interacted with the object during its Mars passage. Such an event would need to leave traces in orbital solutions timing residuals or unexpected velocity changes. Interstellar objects are tracked globally by independent observers. Coordinated falsification across these networks would be extraordinarily difficult. Current orbital fits do not show discontinuities consistent with external manipulation. Absent such signatures, the hypothesis lacks grounding. There is also the notion of unseen observation rather than interaction. Military or intelligence sensors may have monitored the object without public disclosure. This is plausible in principle, because surveillance systems exist outside civilian science channels. Yet plausibility is not evidence. Classified observation does not alter the object's behaviour. It merely limits public awareness of certain data sets. If civilian observations remain internally consistent, the existence of additional classified data becomes irrelevant to scientific interpretation. The comet does not behave differently because it is watched quietly. What distinguishes robust hypotheses from fragile ones is falsifiability. Procedural explanations can be tested against future data releases. Environmental effects can be checked against solar activity records and photometric trends. Composition models can be refined with spectroscopy. Artificiality claims can be challenged by searching for specific non-natural signatures. Hypotheses that cannot be tested drift toward belief rather than analysis. Time plays a critical role here. Interstellar objects move quickly. Observational windows close. Conclusions drawn too early tend to overfit limited data. Astronomy has learned this lesson repeatedly. Initial excitement fades as data sets expand. Patterns sharpen or dissolve. Patience is not passive, it is methodological. The danger lies not in proposing multiple hypotheses, but in treating them as equally likely without regard to evidence. Scientific reasoning ranks explanations by parsimony and consistency. This ranking is provisional, not permanent. It shifts as data accumulates. At present, the ordering favours mundane causes over extraordinary ones, not because wonder is discouraged, but because discipline demands it. There is a historical parallel worth noting. Early cometary science once treated comets as omens, then as atmospheric phenomena, then as solar system debris. Each transition followed improved observation. Interstellar objects are undergoing a similar process. They feel disruptive because they extend the domain of inquiry beyond familiar boundaries. Over time, familiarity will reduce mystique. What remains valuable in this moment is not resolution, but calibration. Understanding how uncertainty propagates helps refine future responses. When the next interstellar object appears, expectations will be shaped by this experience. Institutions will anticipate scrutiny. Observers will coordinate faster. Narratives will still form, but perhaps with greater awareness of their provisional nature. Ultimately, the exercise of weighing hypotheses is less about this single object than about how knowledge advances under constraint. Evidence accumulates unevenly. Silence does not imply absence. Delay does not imply design. The universe does not align itself to human schedules, and neither does understanding. The object continues on its path indifferent to interpretation. What evolves is human perspective. Each discarded hypothesis strengthens the remaining ones. Each confirmed measurement narrows uncertainty. In that narrowing lies progress, not drama. The real signal emerges not from speculation but from convergence. As the object slipped behind the sun from Earth's perspective, attention shifted from immediate observation to the slow work of recovery. Solar conjunction is not an anomaly, but a routine constraint of orbital geometry. When a comet approaches alignment with the sun glare, overwhelms detectors, instruments are protected and observation pauses. For weeks, sometimes months, the object becomes inaccessible. This absence is not silence imposed by policy, but by physics. The post-conjunction phase is therefore decisive. What emerges afterward is not a continuation but a consequence. The object has endured peak solar heating. Volatiles have been released. Dust has dispersed. Any structural weakness has been tested by radiation and thermal stress. Observations made after this period carry the imprint of everything that occurred earlier, including during the Mars window. In this sense, conjunction does not erase evidence, it delays it. When 3i Atlas reappears, several forms of verification become possible. Ground-based telescopes regain line of sight, allowing astrometry to extend the observational arc. Each new position measurement refines the orbit. If the object experienced unusual forces earlier, residuals will appear when models are updated. Orbital mechanics is unforgiving. Small deviations accumulate. They cannot be hidden indefinitely. Photometry provides another layer. The brightness of a comet over time follows characteristic patterns. Activity rises as solar distance decreases and falls afterward. Deviations from predicted light curves, signal changes in rotation fragmentation or outgassing behavior. These are not subtle effects. They register across independent instruments and observers. If something unusual occurred during early October, it should manifest as an after effect rather than a vanishing act. Spectroscopy offers deeper insight. As the coma reforms and evolves post-conjunction, the relative abundance of gases can be measured. Water carbon monoxide, carbon dioxide, and trace metals each leave distinct signatures. Ratios matter more than presence. Normal cometary chemistry is well documented. Departures from it require explanation. Repeated detection across facilities strengthens confidence. Isolated detections invite caution. The recovery phase also enables cross-validation. Space-based instruments, if available, observe without atmospheric distortion. Ground observatories contribute volume and redundancy. Amateur astronomers add density of coverage. The convergence of these sources is critical. When multiple observers report consistent results, uncertainty contracts. Disagreement demands investigation, not assumption. This is where procedural delays lose significance. Data release timing becomes less important than data coherence. Even if some observations are late, their integration into a growing dataset reveals where the gaps mattered. An interstellar object cannot selectively conceal its properties. Physics enforces consistency. There is also an archival dimension. Once an orbit is sufficiently refined, past positions can be predicted with higher accuracy. Image archives from surveys and missions can be searched for pre-discovery detections. Each recovered image extends the timeline backward, improving confidence in trajectory and behavior. This process has repeatedly transformed transient mysteries into well-understood objects. Historical precedent supports this approach. Comets once thought lost were recovered decades later through archival searches. Asteroids initially mischaracterized were reclassified as data accumulated. The narrative arc of uncertainty followed by resolution is common. The difference here is the emotional weight attached to interstellar origin, which amplifies every delay. The recovery period also tests claims made during absence. Assertions of missing data, suppressed imagery, or anomalous behavior can be checked against released material. Time-stamped files, metadata, and calibration logs provide context. Science leaves traces. If something occurred, it will appear in the record, even if interpretation evolves. What matters is not speed, but completeness. Rushed conclusions drawn before conjunction risk misattribution. Post-conjunction data acts as a filter, removing explanations that cannot survive extended scrutiny. In this way, waiting is not passive, it is a methodological requirement. The psychological shift during this phase is subtle. Urgency fades, curiosity remains. The absence that once fueled speculation becomes a quiet interval of preparation. Instruments wait, analysts plan. The object continues its path unchanged by attention. When observation resumes, the question is not whether the mystery persists, but whether it sharpens. Clear anomalies grow clearer. Weak claims dissolve. The field narrows. This narrowing is the hallmark of progress, even when outcomes are mundane. In the long view, post-conjunction recovery is where interstellar objects become part of comparative science, rather than singular events. Each measured parameter joins a growing dataset. Patterns emerge across objects. Diversity replaces novelty. The extraordinary becomes contextual. For 3i Atlas, this phase will determine its place in that continuum. Whether it resolves into a typical interstellar comet or retains distinctive features, the answer will rest on accumulated evidence, rather than inference drawn from silence. The universe offers no shortcuts. Understanding arrives in increments carried forward by persistence rather than urgency. As attention broadened beyond current measurements, a quieter line of inquiry emerged, one that did not depend on future observations at all. Space science carries a long memory preserved not in headlines but in archives. Vast quantities of data are collected every day by surveys, spacecraft and instruments, whose primary targets have nothing to do with interstellar visitors. Within that accumulated record, objects sometimes appear long before they are recognised. Discovery in this sense is often retrospective. For 3i Atlas, the official discovery date marks only the moment when motion was noticed and classified, not necessarily the first time photons from the object struck a detector. Before July 2025, telescopes across the world were already imaging the regions of sky through which the object passed. Survey programs such as Pan-STARRS Atlas itself, the Zwicky Transient Facility, and other wide-field instruments continuously record faint points of light. Most are catalogued, most are ignored, and some only gain significance later. Once an orbit is established with sufficient precision, it becomes possible to run time backward. The predicted past positions of the object can be calculated not perfectly, but accurately enough to search archival images. This process, known as prediscovery recovery, has reshaped the histories of many comets and asteroids. Each recovered frame extends the observation arc, reducing uncertainty and tightening models. What once appeared sudden becomes gradual. The implications of such recovery are subtle but powerful. If 3i Atlas appears in images taken weeks or months before its recognised discovery, those detections provide independent confirmation of its brightness, activity level and trajectory. They anchor interpretations in data that predate the heightened attention and speculation. They offer a baseline uncontaminated by narrative momentum. Space-based archives also hold promise. The Hubble Space Telescope, for example, has imaged vast regions of the sky over decades. Its archive is public searchable by coordinates and date. Even when Hubble was not targeting a comet, background fields sometimes contain transient objects. Similar possibilities exist for infrared surveys, calibration frames, and test observations from planetary missions. Mars orbiters themselves accumulate data beyond their primary objectives. Wide-angle context images, instrument calibrations, and starfield checks are routine. In rare cases, distant objects pass through these fields unintentionally. The probability is low, but not zero. With refined ephemerids, even unlikely intersections become worth examining. The search is laborious, but science often advances through patience rather than luck. Archival work carries an additional benefit: it decentralizes interpretation. Once data is public and historical, it becomes immune to real-time pressure. Analysts working years later have no incentive to embellish or suppress. Their task is simply to measure and compare. In this way, archives function as a stabilizing force, counteracting the distortions of immediacy. There is precedent for this approach. Comets, once thought newly arrived, have later been traced to earlier appearances. Asteroids initially classified as near-Earth objects were re-identified as long-period visitors after archival recovery. Each case narrowed uncertainty by extending temporal context. Time in science is often the most valuable variable. The same logic applies to interstellar objects. Their rarity makes each detection feel isolated, but archives can reveal continuity. Even a single prediscovery frame alters interpretation. It constrains brightness evolution. It confirms direction of travel. It reduces reliance on extrapolation. In doing so, it weakens speculation that thrives on gaps. Community involvement is central to this process. Amateur astronomers and citizen scientists routinely participate in archival searches. Equipped with modern software and access to public databases, they contribute meaningfully to orbital refinement. Their work is not ancillary, it is integral. Distributed effort compensates for limited institutional bandwidth. This collaborative model also reinforces transparency. When many independent analysts examine the same historical data, selective omission becomes implausible. Disagreements surface, methods are compared, errors are corrected. Confidence emerges not from authority but from convergence. The search for archival evidence also reframes expectations. It shifts focus from dramatic revelation to incremental understanding. A faint streak in an old image may not be exciting, but it is informative. It grounds theory in observation. It replaces narrative urgency with empirical calm. For 3i Atlas, the value of this approach lies not in confirming or denying extraordinary claims, but in contextualizing the object within known populations. If archival data shows consistent cometary behavior across time, then novelty diminishes. If it reveals unexpected stability, variability, or brightness trends, those findings can be investigated without haste. There is also a philosophical dimension. Archives remind us that discovery is not always an event but a realization. Objects move through the universe regardless of attention. Human recognition lags behind reality. Science advances when recognition catches up, not when reality changes. In this sense, legacy data acts as a quiet corrective. It resists the illusion that significance begins at the moment of naming. It reveals continuity beneath apparent suddenness. It anchors understanding in duration rather than surprise. As more interstellar objects are detected in coming years, archival methods will become routine rather than exceptional. Each new arrival will trigger automated backward searches, extending arcs almost immediately. What feels novel now will become standard practice. The mystery will shift from whether such objects exist to how diverse they truly are. For the present case, the archives wait patiently. They hold whatever they hold indifferent to expectation. Whether they reveal faint confirmations or remain silent, they will contribute clarity. In science, even absence is data. The past, once examined carefully, often answers questions the present cannot. As the investigation reached its final phase, the story of 3i Atlas resolved not into certainty but into perspective. This is often how scientific episodes truly end. Not with definitive answers, but with a clearer understanding of scale limitation and context. What began as a rare detection and unfolded through silent speculation and gradual analysis ultimately revealed more about the process of knowing than about the object itself. Interstellar objects challenge a fundamental habit of thought. Humans are inclined to treat what arrives from elsewhere as intentional, exceptional, or meaningful by design. Yet the universe operates without regard for interpretation. Bodies are ejected from planetary systems as a matter of dynamics. They drift for millions of years indifferent to whether they are ever noticed. When one happens to cross our path, significance is assigned after the fact not carried within it. The passage of 3i Atlas reinforced this distinction. Its trajectory was consistent with gravitational physics. Its activity responded to solar energy. Its evolution followed patterns that, while unfamiliar in detail, remained grounded in known processes. The sense of mystery arose not because the object behaved impossibly, but because it occupied a domain where human experience is thin. Lack of familiarity was mistaken for lack of explanation. Over time, the accumulation of data narrowed the range of plausible interpretations. Extreme hypotheses lost force as mundane explanations gained coherence, not because imagination was discouraged, but because evidence exerted pressure. This is the quiet mechanism by which science advances. Ideas are not defeated by argument, but by irrelevance when data no longer supports them. The broader significance of the event lies in what it revealed about readiness. Scientific instruments proved capable. Detection pipelines functioned as intended. Where friction emerged was an alignment between observation and communication, between public expectation and procedural reality. These frictions are not failures of science, but features of systems still adapting to a new observational era. Interstellar astronomy now exists in that transitional space. The first detections feel singular. Each carries emotional weight disproportionate to its data. As numbers increase, the weight will distribute. Familiarity will grow. What now seems extraordinary will become comparative. This does not diminish wonder. It grounds it. There is historical comfort in this trajectory. Many fields have passed through similar phases. Early geology grappled with deep time. Early biology resisted evolution. Early cosmology struggled to accept the scale of the universe. In each case, expansion of perspective preceded consolidation of understanding. Interstellar objects belong to this lineage of conceptual growth. What remains unresolved after 3 Atlas is not a mystery of intent, but a question of diversity. How many forms can planetary debris take? How strongly do formation environments imprint on small bodies? How representative is our own system of the galaxy at large? These are questions that cannot be answered by a single object, no matter how intriguing. The temptation to extract meaning from coincidence is understandable. Timing invites narrative. Silence invites suspicion. But science operates most effectively when it resists these impulses. Coincidence is evaluated statistically, not symbolically. Silence is interrogated structurally, not emotionally. When this discipline is maintained, uncertainty becomes manageable rather than destabilizing. In retrospect, the episode surrounding 3i Atlas may be remembered less for what was hidden or revealed, and more for what it clarified about expectation. It clarified that interstellar objects will continue to arrive without warning, that observation windows will remain narrow, that human systems will occasionally misalign with cosmic events, and that none of this implies intention beyond physics. The object itself has now receded beyond meaningful reach, returning to the background flow of the galaxy. It carries with it no message, no confirmation, no conclusion. What it leaves behind is adjustment of models of assumptions of preparedness. Adjustment is rarely dramatic, but it is durable. Future detections will benefit from this adjustment. Response protocols will improve, communication strategies will adapt, interpretive frameworks will widen. When the next interstellar visitor passes close to a planet or aligns with a sensitive window, the experience of 3i Atlas will inform reaction not as a warning but as precedent. In this sense, the story closes quietly, as many scientific stories do, not with revelation but with integration. The object becomes a data point, then a reference, then part of a pattern. Its individuality fades as its contribution persists. Science does not require mystery to be meaningful. It requires honesty about what is known and humility about what is not. The passage of 3i Atlas reaffirmed both. It reminded observers that the universe is vast enough to surprise without conspiring, complex enough to challenge without deceiving, and indifferent enough to demand patience. What endures is not the object but the posture it encouraged. A posture of measured curiosity, of skepticism without cynicism, of openness without projection. In that posture, understanding advances steadily, even when answers remain incomplete. And that is where the story naturally settles, not in certainty, but in continuity. As the broader narrative surrounding 3i Atlas settled into academic memory, its most enduring contribution emerged not from what it revealed about the object itself, but from how it reshaped the boundaries of expectation. Scientific progress is often driven less by discovery than by recalibration. When assumptions are adjusted, even slightly entire fields shift in response. This event functioned precisely in that way. One of the clearest adjustments concerned rarity. For much of the 20th century, interstellar objects were treated as statistical curiosities, possible in theory but unlikely in practice. Their detection was expected to be so infrequent that dedicated preparation seemed unnecessary. The appearance of multiple confirmed interstellar visitors within a relatively short span challenged that premise. It suggested that the limiting factor was not scarcity but sensitivity. This realization carries implications that extend beyond small body research. If interstellar debris is more common than previously assumed, then planetary systems across the galaxy must be dynamically active. Ejection is not an exception, it is a consequence. Planets migrate, resonances destabilize debris disks, and material is expelled into interstellar space as a natural outcome of formation and evolution. The solar system, once thought stable and representative, becomes one example among many. In this broader context, 3i Atlas no longer appears anomalous. It becomes a sample, limited, imperfect, but real. Its properties gain meaning only when placed alongside others, yet to be observed. This reframing diminishes the temptation to overinterpret any single feature. Density estimates activity patterns and compositional hints remain provisional, awaiting comparison. Such comparison is the foundation of mature science. Fields evolve from descriptive to statistical once datasets grow. Early astronomy catalogued stars one by one. Later, it classified populations. Planetary science followed the same path, moving from singular worlds to systems. Interstellar astronomy is now at the threshold of this transition. The discomfort surrounding early cases reflects that growing pain. Another lasting implication lies in methodology. Interstellar objects force efficiency. Their velocities are high, their paths are unrepeatable, observation windows are short. This demands rapid response, flexible scheduling and coordination across institutions that were not originally designed for such immediacy. The experience surrounding 3 Cygni Atlas exposed both readiness and rigidity within existing frameworks. In response, discussion has increasingly turned toward automation not just in detection, but in follow-up. Pre-approved observation triggers cross-agency data sharing, and standardized alert systems reduce reliance on ad hoc decisions. These measures do not eliminate uncertainty, but they ensure that uncertainty arises from physics rather than delay. Equally important is the cultural adaptation required within science communication. Interstellar events attract public interest precisely because they touch deep questions about origin and context. Silence, even when justified, is interpreted emotionally rather than procedurally. The lesson is not that science must speculate to satisfy curiosity, but that it must explain process as clearly as it explains results. Transparency about uncertainty is not a weakness, it is a stabilizer. When observers understand why answers take time, patience increases. When they understand what data can and cannot show, speculation loses force. This clarity becomes increasingly important as discoveries move faster than interpretation. The case of 3i Atlas also underscored the value of restraint. In an era of rapid dissemination, there is pressure to attach meaning quickly. Yet history repeatedly shows that early interpretations are often revised or discarded. The most robust conclusions are those that survive delay. By resisting premature synthesis, the scientific community preserved flexibility rather than sacrificing credibility. At a deeper level, interstellar objects subtly alter humanity's self-conception. They are reminders that the solar system is porous, not isolated. Matter moves between stars. Histories intersect invisibly. Earth exists within a stream of galactic exchange far older and larger than civilization. This perspective does not diminish local significance, it situates it. The absence of extraordinary conclusions about 3i Atlas may therefore be its greatest strength. It demonstrated that not every unfamiliar phenomenon requires radical explanation. The universe is vast enough that novelty can arise naturally. Accepting this reduces the impulse to project meaning where evidence does not support it. Over time, early interstellar detections will recede into background knowledge. They will be cited, compared and contextualized. Their individual narratives will blur into collective understanding. This is how scientific memory works. What remains is not the excitement of first encounter, but the structure it helped build. Future generations of astronomers will inherit a field better prepared for such visitors. They will look back on this period as formative, marked by uncertainty, but also by rapid adaptation. The challenges faced during the passage of 3i Atlas will appear modest in hindsight, yet essential in shaping response. In that future, the object itself will be little more than an entry in a catalogue. Its trajectory will be known, its basic properties summarised. Its role will be historical rather than investigative, and that is appropriate. Science advances by absorbing the unfamiliar until it becomes ordinary. The enduring lesson of this episode is therefore not about secrecy, coincidence, or revelation. It is about scale. Scale of space, where distances render rarity deceptive. Scale of time, where understanding unfolds gradually. Scale of systems, where human institutions struggle to match cosmic indifference. What remains is a quiet confidence that such challenges are navigable. Each interstellar object refines not only models, but mindset. With each passage, preparedness improves, interpretation steadies. Curiosity remains, but it becomes disciplined. In this way, the story continues not driven by a single object, but by the steady accumulation of encounters that together redefine what it means to observe a universe that is not bounded by one star. So let's come full circle. Dreamer, we began this journey in a moment of silence, a pause in human systems set against the steady motion of the cosmos, a shutdown on Earth, a visitor drifting past Mars, and between them a question that asks not for urgency, but for patience. What we've seen is not a revelation carved in stone, but something quieter. The truth that science moves at the pace of evidence, not speculation. That absence does not always mean intention, and that mystery often lives longest in the space where data has not yet finished speaking. 3 Atlas continues its path now rounding the sun, carrying no message we can hear yet, only light motion and time. Telescopes will turn again, numbers will settle, papers will be written. Some answers may arrive softly, others may never arrive at all. And that is part of the wonder, because to observe the universe is to accept humility. We are small beneath these distances, brief beneath these orbits, and yet we are here able to notice, able to measure, able to wonder. That alone is something rare. If tonight left you with questions, let them rest gently. The universe does not demand resolution from us. It only invites attention. It keeps unfolding long after we close our eyes. Thank you for drifting through this story, for listening closely, for keeping watch beneath the same sky. Rest well. Stay curious. The universe will keep moving, and when you're ready, the next whisper will still be waiting.